An ordinary general annuity occurs or is used to calculate the future or the present, we can go one way or the other, it doesn't matter, of a payment stream that's made at the end of the payment interval. By definition, an ordinary annuity, the payment is at the end of the payment schedule. When the payment interval and the compounding frequency are different. And 9 times out of 10, they're going to be different. What does that mean, you say? Well, what exactly are you talking about in terms of the payment schedule being different? Well, let's just go, I'm just going to hop to an example problem. So here we go. The preferred shares of Dominion Trust will pay 75 cents per share dividend at the end of every calendar quarter until it's redeemed, 8.5 years from now. On the redemption date, the shareholder will receive $40 par value of each share in addition to the last regular dividend. What is the fair market value of the share if the preferred shares with similar risk are currently taking in a rate that is 6.5% compounded semi-annually? Okay, that sounds like a bunch of mush, but the fact of the matter is you need to look at any problem like this and say, now, is this an annuity, number one? And we know it is because there's a stream of payments, okay? So there's a stream of payments here. The second thing we have to ask ourselves, is this a simple annuity or a general annuity? A simple annuity, the payment schedule, once a month and so on, matches the compounding schedule. So payments monthly, compounding's monthly. Payments yearly, compounding is yearly, that sort of thing. So we look at this one, and it says that the dividend at the end of every calendar quarter, so effectively 4 times a year it's paying, and the interest, you'll notice, is 6.5% compounded semi-annually. So we've got payments quarterly, and the interest is semi-annually. So we've got 2 different schedules going on here, one for the payment, one for the interest, okay? And that's the trick. That is the thing that you need to really look for in these problems in order to differentiate one problem from another. The payment interval and the compounding frequency are different. That's the takeaway that we need to bring it in. If we're looking at these, a lot of times these are present value calculations. And again, as I say, what we need to be able to do is we need to be able to use the same basic formula that we've used for simple annuities. However, there is one more formula that's brought in that affects the value of I, okay? The value of I being the periodic interest rate. And in order to calculate the value of I, we call it I2 for short. So in order to calculate that value of I, the formula is right there on the bottom. If you look at it, you'll see it's I2 equals 1 plus I, the periodic interest rate that you're reading right off the problem, to the value of C minus 1. Okay. So we know the I is the periodic interest rate as stated in the problem. What's this C? Well, C is something we have to calculate. C is the number of compounds per year divided by the number of payments per year. Okay? So the compounds, how many times the interest compounds, divided by how many payments per year. So that's the real trick to these problems, is you need to do this subtle extra calculation that calculates I2. And I2 is the periodic interest rate for a general annuity. And in order to calculate I2, you got to take the value of I, which is stated in the problem, and 1 plus I to the power of C, and C is calculated by the number of compounds per year divided by the number of payments per year. Now, it sounds more complicated than it actually is, but the fact of the matter is there are a couple of extra steps to this type of problem that you need to be aware of. So you got to be able to distinguish the problem, number one, and then be able to contemplate those steps, number two. So in order to do this, we could calculate, for example, the present value. So here's the present value formula. In the last one I showed you, in the one we did last week, we did future value formula. Again, these two formulas are effectively the two that you need to use. So here we're calculating the present value. So the present value is the payment times 1 minus 1 plus I2. Remember, we just did this calculation for I2 over here, to the power of minus n over I2. So again, we put in I2 twice. And in order to calculate I2, you need to use this formula right here, 1 plus I to the C minus 1, and then C is calculated by the number of compounds and the number of payments. So we can, that's the present value calculation. The future value calculation, do the exact same thing. Got to calculate the value of C, and then we can plug C in to get the value of I2, and then we just kind of plug it into the future value formula that we used last week. Same formula, but we're replacing I with I2. Okay? So the hardest part of these is recognizing, do I have a general annuity here, or is it a simple annuity? And the trick is that you need to look at the payments, how often they're occurring, and you need to look at the interest, how often is it compounding. If it's the same, it's simple. If it's not the same, it is what's called a general annuity. Here, for example, we're calculating the value of I. All this is calculating this I. To a 5-figure X, you calculate the periodic interest rate that matches the payment interval 4. So here we got semi-annual payments and compounding annually. So right off the bat, semi-annual payments twice a year, and the compounding is annually. So we got annual compounds, semi-annual payments. That is by definition a general annuity. Okay. So what we need to do then is we need to be able to incorporate this new formula that we've just learned, which is to calculate the value of I2, which is effectively what we're doing. Now, in order to do that, first of all, we need the value of I, and the value of I is 5% compounded annually. So I is 5% divided by 1. That's 5%. Okay. And then we got to go calculate this thing of C, which is over here. I showed you that in order to calculate the C is number of compounds per year divided by number of payments per year. So number of compounds is 1 compound per year, compounded annually, divided by 2 payments per year. That's 0.5. We take that then and we put it in this value of C. So it's I2 equals 1 plus the value of I, which is 5%, so 1.05 to the power of 0.5 and minus 1, and that will give you 2.4695 per half year. So effectively, it's a revised formula for the value of I, called I2. Then we just take that number and we plug it right into the present value formula or the future value formula, whichever one you're using. In the case of B here, monthly payments discounted at 6% compounded quarterly. Okay, first thing we need to do is look at it and say, is this a simple or a general annuity? Well, it's monthly payments compounded quarterly, different. So we need to be able to say, okay, this is a general annuity. And in the general annuity, we need to calculate the value of I2. So what we're going to do here is we're going to say, okay, well, the value of I is 6%, and it's compounded quarterly, so the value of I is 6% divided by 4, so that's 1.5% per quarter. Then we got to calculate this value of C, which is the little sub-calculation that we need to do, and the number of compounds per year is 4, the number of payments per year is 12, and that's 0.33333. Then we just throw that into this formula here in order to calculate the value of I2. I2 is 1 plus I to the power of C, so minus 1. So that's 1.015 to the 0.3333 minus 1, and that comes out to 4.97%. If you want to look at another example that's worked out here for us, if $1,000 is invested at the end of the year at 8% compounded semi-annually, what will be the total value of periodic investments after 25 years? So we've got $1,000 going in now, and it's going to be invested at the end of every year. So, okay, so $1,000 every year for 25 years. The compounding is semi-annually, and the whatever you call it, the amount of money that you put in, I'll call it the payment, is every year. So this is a general annuity. So we need to be able to then calculate the value of C. C is 2 compounds a year divided by 1 payment a year, which is a value of C of 2. We throw it into the I2 formula. I2 equals 1 plus I to the power of C, which in this case is 2 minus 1. So that's 1.04 to the power of 2 minus 1, which is 0.0816 per year. And we just run that number through the formula. So in the value of I or I2 in the formula, we just put in 1.0816. And that works true to do the calculation. Exercise 10.4 or 11.4, depending on what book you're using. So it says the nominal interest rate associated with the ordinary general annuity is 3% compounded annually. Rounded to the nearest thousandth, what is the corresponding periodic interest rate that matches the payment interval for? Okay, so effectively, right here, we have got a 3% compounded annually rate. So what we're going to do is we're going to say, okay, depending on the scenario, let's figure out how we can calculate the value of I2. So I is 3% because it's compounded annually, 3 divided by 1. But the I2, because the semi-annual payment is different than the annual, we need to calculate the value of I2. So in order to do that, what we need to be able to do is to calculate this value of I2, which is 1 plus I to the C minus 1. And C is the number of interest payments during the year, interest compounds during the year, by the number of payments per year. So what we got is number of interest is compounded annually. So that's 1. And number of payments during the year, seeing it semi-annually, is 2. So what we've got here is 1 over 2. So the value of C is 0.5. That's the value of C. So we take that 0.5 and we put it in the value of C here in the I2 formula. So I2 equals 1 plus, and the I, the version of I, is 3 divided by 1, 0.03, to the power of C, which is calculated here, minus 1. So I2 is 0.014889. So that's how that is calculated for A. So let's take a look at B, which is quarterly payments. So we've got 3% compounded annually and quarterly payments. So the trick is, in terms of this one, is we need to be able to figure out the value of I2. So in the case of B, in order to calculate C again, it's number, and in this particular instance where it's quarterly payments, there's 1 interest per year and 4 payments per year. So 1 over 4 is 0.25. So C is 0.25, 0.25 in the formula. I2 equals 1.03, which is 3% divided by 1. That's where that 03 came from, to the minus 1. And that gives you an I2 of 0.00742. C is monthly payments. Okay, so we've got this 3% compounded annually. What if we're in monthly payments? So we got the monthly payments, 12 payments per year. And this then is C is number of interest conversions per year is 1. Number of payments per year is 12. That gives us 0.03 as the value of C. We take that, plug it into the I2 formula. So there's the value of C. 1.03 to the power of 0.03 minus 1 is I2 of 0.002466. I want to take a look at number 13. Lacey purchased a car. Okay, so Lacey purchased a car with $1,200 down at the end of the month, payments of $352 for 4 years. What is the purchase price of the car if she has financed it at 7.55% compounded semi-annually? So what we're here looking for is the original price. So she's paying $1,200 down in the month payments $352 for 4 years. Okay, so what we need to be able to do in this one is to come up with some sort of a timeline in order to really get yourself head around this. So Lacey purchased a car, so it's $1,200. If we were to draw a timeline on a sheet, $1,200 is right away, and the end of the month payments of $352 for 4 years. Now we know, seeing the section we're in, that is going to be a general annuity problem. So first of all, the interest is stated at 7.55%, and it's semi-annually, so you can divide that by 2, and that will give you a value of I of 0.03775. And we asked ourselves how many payments there are. Well, as I said, it's 4 years, 12 payments a year is 48 payments. Value of C, as I just said, is dealing with the number of interest conversions, which is 2, and the number of payments, which is 12. It gives you that nice fraction, which is 1/6, which is 0.11666, and so on. In order to calculate the I2, then you just throw that bit of data in here. So 1 plus I, and we calculate the I is 0.03775 to the power of C, which we calculated at 0.16666, and minus 1. And that will give you 0.006195. So then what we're looking for in this particular case is the present value, because we're looking for how much did you pay for the car. The payment is 352. 1 minus 1 plus I2, which we know is 0.006195, is calculated, to the N, which is the total number of payments, which is 48, over I2 again. This works out to $14,576.73. That's the present value of payments. Saying she made the very first payment today, which is the present, we just subtract out the $1,200. Mr. and Mrs. Kitts is contributing to an RESP that would set up for children. What amount would they have in the RESP after 8 years, after contributing $500 at the end of every calendar quarter, sorry. So 4 times a year. If the plan earns 6% compounded monthly. So the payments are going in 4 times a year. The interest is compounded monthly. They're different. So this is a general annuity. How much of the total amount is interest? Number 14, we have the Kenses. They're putting money aside for their children. They have an 8-year window. The amount of the payment is $500 per quarter. The rate is 6% compounded monthly. So one of the first things we need to recognize that the payment is a quarterly arrangement and the compounding is monthly. The moment that we see that should cue us to this is an ordinary general annuity. Okay, they're different, ordinary general. So what we can take away is some of the basic information. Well, the payment is $500. The interest, or I, the periodic rate of interest, is 6% divided by 12, seeing it's compounded monthly. So that's 0.5% per period, which is in decimal format 0.05. The total number of periods, the total number of payments, well, it's 4 quarters a year times 8. So there's a total of 32 payments. That's N. And then we talked about the value of C, and the C is the number of compounds per year of the interest divided by the number of payments per year. So let's take a look. Now, the compounds per year. Well, it says that the interest rate is compounded monthly. So the compounds per year is 12. And it says that it's $500 every quarter. So that's payments per year is 4. So 12 divided by 4 is 3. So the value of C is 3. Then we got to do the calculation for I2. So what we do with I2 is we take 1 plus I, and we calculate the value of I to be 0.005 to the power of C, and we calculate the power of C to be 3. So that's 1.005 to the power of 3 minus 1, which comes to 0.0151. So that's the value of I2. Now, what we're calculating here is to see how much the future value is, because they're saying what it's going to be worth in 8 years. So we plug it into the basic formula for calculating the future value of an annuity. So the payment is 500. 1 plus I2, we've calculated I2 to be 0.0151. To the power n is the total number of compounds that go on during the life of this. Well, we've calculated that to be 32 minus 1, and divide it again by I2. So I2 is 0.0151. If we were to do the math on that, it'd be $20,369.41. So effectively, after 8 years, they'd have $20,369.41 gathered up. Now, we're having done this now, and I'm hoping that you're getting some sense on this. Here are some of the confusing parts in this. We have to calculate this value of I2. And in order to calculate the value of I2, we need to calculate the value of C. Now, C is the number of compounds per year over the number of payments per year. Notice that it is dealing with this C thing. C is a calculation of interest. This is how I remember it. It's a calculation of interest. We're only looking at a year, 1 year, because that's what's happening in the year, effectively. So that's what's going on there with calculating C, which is used to calculate I2. In the main future value formula, the value of N is the total number of compounds for the whole darn thing. And considering we're looking at the future value of the whole darn thing, it is appropriate that N be for the whole darn thing. So we should get that value of N and the value of C. So the two of them are often confused in terms of how to calculate it. So you want to be able to keep it straight in your mind, saying that C is just for the year thing, and the N is for the overall flow of payments. Any questions on that? The part B of that is looking at, bring up my presentation again. Part B of that is, okay, what is the total interest paid? Well, okay, in order to find interest paid, all I got to do is think about what was the original amount of money we're dealing with and what is the time value of money. So if we think about the original money, well, we put $500 a month in for 32 months. Okay, so that would have been, in my mind, $16,000. 500 times 32 is $16,000. We got, though, $20,369. So the difference between what we put in and what's there now must be interest. So we take the $20,369.41, we subtract off the $16,000 which we put into it, and the $4,369.41 difference is then defined as interest. Number 16 says, how much larger will the value of an RRSP be at the end of 25 years if the RRSP earns 9% compounded monthly instead of 9% compounded annually? In both cases, a contribution of $1,000 is made at the end of every 3 months. Okay, so what we're doing here is running two parallel streams. We're looking at the first stream, which is where you got $1,000 every 3 months at the end of the month, put in, and in the first stream, 25 years at 9% compounded monthly, and in the second stream, 9% compounded annually. So two different setups for interest and like. So what we have to do is do a parallel calculation, one for the 9% compounded monthly and one for the 9% compounded annually. So the very first one we're going to do is to take a look at the 9% compounded monthly option of the RRSP. So if it's 9% compounded monthly, we got to be able to say, okay, what is the value of I? Well, 9% divided by 12 would give us the periodic interest rate of I, which is 0.75%, which is 0.0075. The total number of payments, well, it's every 3 months. That's 4 payments a year times 25 years is 100 payments. In order to calculate the value of C, C is the number of compounds per year, and we know the number of compounds per year in this case is monthly compounded, so that's 12. And number of payments per year, we know that there's every 3 months, so that's over 4, so the value of C is 3. Then we can use the value of C to calculate the value of I2. We're going to take 1 plus I, and we know the I is 0.0075 to the power of, and we calculated this amount to be 3. C is the value, C is that's 3 minus 1, and that's 0.02269. So that's that I2. That's the calculation of I2. So that's part A. That's the basic information we need in part A, and we are calculating the future value, so we'll just come back to that in a minute. In the case of B here, we've got the second scenario is 9% compounded annually. So 9% divided by 1 is 9%, and that's 0.09. The number per the whole outfit is 4 payments a year times 25 is 100. Calculation of C is number of compounds per year, which is only 1, and number of payments per year, which is 4. So that's 0.25 or 1/4, which is 0.0025. With 0.025. We can calculate I2 then as 1.1 plus 0.09, which is our calculation of I, to the power of 0.25, which is a calculation of C, minus 1, and that's 0.02177. We take that's I2, we plug that into the future value formula, and way to go. Now, once we've done the future value calculation for both of them, here's the future value calculation of the interest rate that involves a monthly compound. If we plug that through the formula, it's 370,918.47. Okay. If we look at the second scenario where it's only 9% compounding once, the total value of that is 350.3294. So you can see that compounding adds, this multiple compounding adds almost $21,000 worth of difference to the two. But this is effectively how you calculate those.